Okay, in this video we're going to discuss binary and ternary truth tables and functions. So here we have a binary function. Here we have a 2-variable function a and b, a 3-variable function a, b, c, and a 4-variable function a, b, c, d. In each case there is an f chosen, which is arbitrarily chosen, just to represent what the function may look like. We have variables or inputs a and b here for a 2-input function, a, b, c for a 3-input function, a, b, c, d for a 4-input function. Now I'm going to discuss how to generate the input combinations for a and b for the 2-variable function, then the 3-variable, then the 4-variable. So we start off with 0, 1 and repeat the pattern down. That's input variable A. Input variable B, we repeat the pattern but in groups of 2, so 2 zeros followed by 2 ones. For a 3-variable function, variable A follows the pattern 0, 1, 0, 1 again, a similar pattern to this all the way down. Variable B follows the pattern 2 zeros followed by 2 ones all the way down and repeats the pattern. For variable C, you have 4 zeros followed by 4 ones. For the 4-variable function here, f, a, b, c, d, A follows the pattern 0, 1 and repeats. B follows the pattern 2 zeros by 2 ones and then repeats. C follows the pattern 4 zeros followed by 4 ones and repeats. And D follows the pattern 8 zeros followed by 8 ones. Now, instead of writing all the combinations this way, this method allows you to generate all the input combinations. And starting with 1, the column to the left is twice the number of consecutive zeros and ones as the column to the right. So here you have 1 0, then 2 zeros and 4 zeros, and then the pattern repeats. Here you have 1 0 followed by 2 zeros followed by 4 zeros followed by 8 zeros. If you had a variable e here for a 5-variable function, you would have 16 zeros followed by 16 ones. Okay, that's 2 variables. Let's just mention f in each case was arbitrarily chosen just to represent what a function may look like. It consists of zeros and ones for binary base 2. Here we have a ternary functions base 3. Here we have a 2-variable function and a 3-variable function here. I've split this into 3 because I couldn't fit all the listings in one truth table, so I've split into 3 just so I can fit it on A4 paper. Here we have f for a 2-variable function, consists of 0, 1s and 2s, and input combinations A and B. Now A follows the pattern 0, 1, 2, 0, 1, 2, 0, 1, 2, and B follows the pattern 3 zeros followed by 3 ones followed by 3 2s. Again, the rule is you start with 1 of each one and then you repeat it 3 times. So 1 0 there, 3 zeros there, followed by 3 ones followed by 3 2s. For the 3-variable function a, b, c, the same pattern arrives, 0, 1, 2, 0, 1, 2, 0, 1, 2. Same deal here. And pattern B follows 3 zeros, 3 ones and 3 2s. And the same for pattern B here. And for column C, it's 9 zeros followed by 9 ones followed by 9 2s. So again, you start with 1, then it's 3 times the number of consecutive digits. So 3 there, 9 there. So, okay, if you let B be the base, the number of consecutive digits in the column is B times the number of consecutive different digits in the column to its right, started with 1, which is what I've said here. So let n be the number of variables, a, b, c, 3 variables, a, b, 2 variables. The number of rows in the truth table is n equals b to the n. So basically 3 squared, 2 variables, n equals 2, 9 rows of the truth table. Here we have 3 base 3 variables, 3 digits, 0, 1, 2, n equals 3 inputs, so 3 to the cubed is 27 rows of the truth table. Yeah. And if we go back to the binary one, we have binary 0 and 1, 2, base is 2, 2 inputs, 2 squared is 4, 2 cubed is 8 for 3 inputs, and 2 to the power 4 is 16 for 4 inputs. A 5 variable input would have 32 rows of the combination of the truth table. Okay, now we get on to the Boolean functions themselves. Here we have an AND function. Inputs A, B, generated as showed before for a binary truth table. And the output, instead of F, we have A and B, which is the AND function for variables A and B. And the way you complete the truth table is to first look at the inputs, and any time you get a 0 on the input, on any of the inputs, you get a 0 on the output. That's step 1. And step 2, fill in the remaining space with a 1. So 1 and 1 equals 1. For a 3 input AND function, you have A, B, C input variables. The function is A and B and C. Step 1, look for the zeros on any of the inputs and put it on the output. And lastly, the only combination left is when all the inputs are 1, which the output is a 1. Right, here we have an OR function for 2 variables, 2 input OR, A and B. Here we have the input combinations A and B as shown before. Here the function is A or B, which has this output combination. So the way you fill in the truth table is to look for the 1s on any of the inputs and fill the output with a 1. That's step 1. And step 2, you fill the remaining output with a 0. That's when all the inputs are at 0. For a 3 input OR, inputs A, B and C variables, you've got A or B or C. You look for a 1 on any of the inputs and you fill that with a 1. That's step 1. And then step 2, you fill in the remaining 0 when all the inputs are 0. Here we have an exclusive OR function. Now these functions are generally made in electronics terms with 2 inputs only. So we have the input variables A and B here, and the output is a 1 if and only if one output or the other output is a 1, but not both at the same time. So 0 there, 1 there, 1 there, 0 there. And here we have the NOT function, which is a unary operator, 1 input. In reply to 0, 1, you get the output 1, 0. So basically it's not, whatever that is, it's the other. It's not A. Not A is signified by a bar at the top. Now we go on to ternary functions, which is base 3 logic system. Those functions I've described earlier for binary were Boolean, the AND, the OR, exclusive OR and the NOT. They were Boolean functions. These are ternary functions. These are multiple valued logic functions. Multiple valued logic describes any logic system with a base of 3 or more, and binary is base 2. So we have the minimum function here. Here we have generated A and B, the truth tables, 0, 1, 2, 0, 1, 2, 0, 1, 2, 3 zeros, 0, 1, 3 2s. And we have the output here for A and B. Call it minimum function because the output takes the minimum of whatever is on its inputs. So it's a similar process to generate the output of the function. Step 1, look for zeros on the inputs and fill them on the output and leave the rest blank. Step 2, next look for the ones, there, fill them in, and lastly look for the 2s. For the minimum function, the 2 will only occur when all the inputs are on 2. So I called it A and B, but really it's a minimum function. It's the ternary minimum function. The AND function in Boolean, in binary, would be the binary equivalent of the minimum function. So it's a similar process to generate the output of the truth table. Here we have the maximum function. This is equivalent to the, well, in the binary case, the maximal function is the OR function. So we have inputs A and B, A and maximum of B, A or B if you like. And we have the inputs A 0, 1, 2, 0, 1, 0, 1, 2. And the outputs there for B, 0, 0, 0, 1, 1, 1, 2, 2, 2. Now to fill in the maximal function, you look for 2's on the inputs and you fill in the output with a 2 whenever there's a 2 on the input. So that's step 1. Step 2, next you look for the 1's, here, for the remaining outputs that aren't a 1. Haven't been filled in, sorry, they're a 1. And next you fill in the last input, which is a 0. A 0 happens when all the inputs are 0. Here we have the sum and product function. This is Reed-Muller logic for base 3, ternary. Reed-Muller logic relies on the sum and product functions to generate the output of the truth table, to generate a function, sorry. So here we have a 2-variable input sum function, A and B, or A plus B, sorry. Here is the input variables A and B, that's the truth table for it. And as you can tell, it's just a straightforward sum modulo 3. So 0, 0 is 0, 0, 1 is 1, 0 plus 2 is 2, 1, 1 plus 1 is 2, 1 plus 2 is 3, which is 0 modulo 3. So using the sum modulo 3 arithmetic, 2 there, 0 again, and 2 plus 2 is 4, which is 1 modulo 3. Here we have the product function generating the same method of the input variables, and the times, as you would expect, 0. Anything 0 is 0. Anything times 0, sorry, is 0. 1 times 1 is a 1, and 1 times 2 is a 2. And here we have 2 times 2 is 4, which is 1 modulo 3. Here we have some unary operators. Here we have A squared, which is A times A. So 1 times 1 is a 1, 0 times 0 is a 0, and 2 times 2 is a 1. Here we have twice A, which is 0, 2, 1, twice A squared, 0, 2, 2. A plus 1, 1, 2, which is 1 plus, this is the successor function, and this is the predecessor function. In response to 0, 1, 2, we get 2, 0, 1 for A plus 2. So that is for Reed-Muller logic base 3, ternary. Here we have the difference of function. Now I've put this function in only because it's useful for one purpose. The output gives the difference of whatever is on its inputs. It's only a 2-input function. So why do it? Well, for a start, it's useful when for comparing when the inputs are equal, because in each case the difference will be 0. So as you can tell, the output is just the difference between the two inputs, ignoring the sign. So a minus b, a minus b, for example, would be 1 minus 2 would be minus 1, but ignore the sign, so it's 1. So, two valid unit operators. This is for a ternary algebra based on these operators, which are two valued. Basically, the output A1 is a 1 when A0 is 0 and 0 otherwise, and A2 is a 2 when A is 0 and 0 otherwise. So here we have the unit operators, which are with the ternary multiple valued algebra. The successor A just adds 1 to the input, and adding 1 to 2 modulo 3 is 0. Here's a predecessor function which takes 1 away from the input A, and taking 1 away from 0 equals 2. 1 away from 1 is 0, 2 away from 1 away from 2 is 1. The diametrical inverter, well, basically it just reverses the order of the truth table A in reverse order, and it's usually represented by a barrel on the top, or I have in this case here. So a recap: for the AND function, the Boolean AND function base 2 binary, also the binary product function, which is I've shown in the ternary case, and the binary minimum function. The OR function is the binary maximal function. The exclusive OR function is the binary sum function and the binary difference of function as well. And the NOT function is also the binary successor function, the binary predecessor function, and the binary diametrical inverter function. Okay, so that concludes the presentation. I hope that made things a bit clearer. I'll be discussing these two valued unary operators, unary meaning one input, and also the successor and the predecessor functions. I'll be using them in a ternary algebra, which is not mine, but I'll describe it and I'll tell you how it works. But these, I won't be using this function, but I'll be using these along with the maximum of and the minimum of functions as well. Okay, thanks for watching. Bye.